Hey there, math peeps. This is Mrs. Marshall, and I'm here with Unit 5, Day 4, and we're going to do some trig identities. And we're going to use these identities to do proofs, our favorite. It's amazing. So let's start with reciprocal identities. Sine theta, and you know theta is just an angle. The reciprocal is the same thing as 1 over cosecant theta. Therefore, cosecant theta, the reciprocal is 1 over sine theta. Cosine theta, reciprocal is 1 over secant theta. And so secant theta, the reciprocal is 1 over cosine theta. And tangent theta, y'all already know, is 1 over cotangent theta. And cotangent theta is 1 over tangent theta. So it's just actually having these identities in one spot, all reciprocal identities. Quotient. Quotient, there are two separate ones, and quotient is when you divide. So to get tangent theta, you divide sine over cosine. But to get cotangent of theta, you're going to divide cosine over sine. And then you have the Pythagorean identities, something new that we haven't really talked about. Your teacher may or may not go a little deeper into this in class, but I'm going to identify the identities and kind of talk through how I got the next one. So the first one is sine squared theta plus cosine squared theta equals 1. The way you get that is because, and don't write this part, do not write this part. When you think of the unit circle, that's a bad unit circle. When you think of the unit circle, okay, that's even worse. Let's start with the circle. Boom. And we think of a triangle. The x-axis is always your cosine. The y-axis is always your sine. And your hypotenuse is 1. So when you're doing a squared plus b squared equals c squared, your a value is typically your x. It doesn't really matter. You can do it as your y going up and down, but it's cosine squared plus sine squared equals 1. And this is, and technically it's 1 squared, and that is where we get the identity from, but we just write sine first, and then we write cosine, and it equals 1. So again, our identity is sine squared plus cosine squared equals 1. To get the other identities from this one, you're just going to solve for each, term separately. So we want to solve for sine squared. So sine squared theta would equal 1 minus cosine squared theta. And then if I solved for cosine squared theta and got that one by itself, cosine squared theta equals 1 minus sine squared theta. And these are identities. We're going to use these again to do proofs. Well, if you start out with the sine squared plus cosine squared equals 1, and you solve for each term individually, that will give you the rest of the sine, or the rest of these sine and cosine identities. But then if you again start with sine and cosine and divide, just doing a different operation, you'll end up with new trig identities. So sine squared divided by sine squared would end up with, well, we'll do cosine. Sine divided by cosine is tangent. And then cosine divided by cosine is 1. And 1 divided by cosine is secant. And all of these are squared. I'm just leaving the word squared off. Just you can say it faster. And now that you've done that, and again, all I did, and don't write this part, was did sine squared of theta plus cosine squared of theta equals 1. And then I divided everybody or everything by cosine squared. And I simplified it. That is what that became, that is what that became, and that is what that became. All right, now that I've done that, I can now take this starting equation and solve for each term. Let's solve for tangent squared first. Tangent squared theta by itself is secant squared theta minus 1. And then 1 by itself is secant squared theta. minus tangent squared theta. And then our last one, if we did the same starting sine squared theta plus cosine squared theta equals 1 identity, this time instead of dividing by cosine, we divide everything by sine, divide by sine, and divide by sine. We would end up getting, well, sine squared theta over sine squared theta ends up equaling 1 plus, and cosine squared theta over sine squared theta equals cotangent squared theta, and 1 over sine squared theta equals, what 1 over sine, you can look at it from the top identities for the reciprocals, but it's cosecant squared theta. And then we solve for each term like we did before. We solve for tangent squared and 1. Now let's solve for 1 and cotangent squared. 1 equals cosecant squared theta minus cotangent squared theta, and cotangent squared theta equals cosecant squared theta minus 1. And these are your Pythagorean identities that come from a squared plus b squared from your triangle on the unit circle. All right, some other identities. We have the cofunction identity, and we have sine of pi over 2 minus theta equals the same thing as the cosine of theta. The cosine of pi over 2 minus theta equals the sine of theta. And now let's move on to tangent and cotangent. Tangent of pi over 2 minus theta equals cotangent theta. The cotangent of pi over 2 minus theta equals tangent theta. And now what's left? Secant and cosecant, and they go together. The secant of pi over 2 minus theta equals cosecant theta, and the cosecant of pi over 2 minus theta equals secant theta. And my last one are the odd-even identities. We're going to split this section in half, and I'm going to give a little space to create a title, a heading for each section. Odd-even identity is also known as the negative identity. So it's dealing with having negative values, identity, or negative sines and cosines, negative thetas or negative x, negative values. So over here we're going to put the odds, over here we're going to put the evens. And what is an odd function? The odd functions are sine of negative theta, and that's thinking about when we were doing even and odd before. When you plug in a negative, if the answer is negative, it is odd. And so sine, that is the case. You plug in a negative theta, the answer you get when you plug in positive theta is negative. And cosecant works the same way, which is sine's inverse. When you plug in a negative theta, when you plug in a positive theta, it equals the same answer, but negative. And then tangent theta, and it's tangent of negative theta, equals negative tangent theta. And let's slide this over a little bit so I can have some room to write it. Negative tangent theta and cotangent negative theta equals negative cotangent theta. I remember these because both of these are the ones where your range ends up being the same spot. So that's like, oh, okay, sine and cosine, or sine and tangent, excuse me, sine and tangent go together because they have the same range when you do inverse. Also, another way I think of it is negative in, and when I say negative in the parentheses, equals the same thing as the negative out. And that is odd. Now we got to do the even. Even is cosine of negative theta equals the cosine of theta And secant of negative theta equals the secant of theta. So in other words, whether you plug in a negative or a positive, both answers are the same. So here's how I remember this one, because this is the only one whose picture is opposite. But also, my little thoughts are, with a negative is the same thing as without a negative. All right. Let's do some examples. We're going to start with the cofunction identities, number 1. And I know it's cofunction because it has this pi over 2 situation going on. So that lets me know that this is cofunction identity. And number 2 is also cofunction identity as well. So you're definitely going to have to use that first sheet like a Bible. Like, it's got to be the rule of all rules when you are using or slash trying to do proofs. So I have my first sheet, right here beside me. You can't see it, but I see it. And I'm going to use that to see how I can rewrite these expressions so that I can get essentially the answer to the expression that they're asking me for. Cosine theta, or cosine of negative theta for the first one, and cotangent theta for the second one. All right, so let's begin. So we got this sine theta and minus pi over 2. Well, the way the rule is written, so take a look at it. The way the rule is written, the pi over 2 is in the front and the theta is in the back. So we need to write it so that pi over 2 is in the front and theta is in the back. Negative pi over 2, don't forget this negative got to go with the pi over 2. And it's still not the rule exactly because it's got to be a positive pi over 2. So let's pull this negative out so we can have a positive pi over 2. But when we pull it out, that's negative theta. And now it's like, gosh, I still got to get that negative out of there. Well, based on the even odd rule, sine of negative theta is the exact same. And so this right here would be considered like our negative theta is the exact same. So I'll put it right here. Sine of negative theta is the exact same as negative sine of theta. And so I can pull that negative out. Negative sine of pi over 2 minus theta. And again, this is considered like our theta. That is in the spot where theta is. Both of those together. All right. Now we have, okay, what does that mean? Well, we have to think about the pi over 2 and the minus theta. Now we got to go back to the cofunction, and it's like, okay, that's just the same as negative cosine of theta. But now I'm trying to get this negative theta up here. Like, oh my gosh, what can I do to get that? Well, cosine of negative theta is the same as cosine of theta. So negative, and I can go ahead and write this as cosine of negative theta. It ends up being the same thing. And therefore, our answer is negative 0.73. And of course, you'll have a chance to practice this multiple times in class. Number 2. All right, let's see its cofunction. It's already set up in the way that we want it with tangent theta, or tangent of pi over 2 minus theta. And then we just got to see what that actually equals. Oh, tangent of pi over 2 minus theta is the same as cotangent of theta. So therefore, if tangent of pi over 2 minus theta is negative 5.32, then cotangent of theta is also negative 5.32. And that is your answer. That one was much simpler than number 1. Now on to some proofs. Or not even necessarily proofs. We're just simplifying, which is going to lead us into proofs. Let's try to simplify these next 2 expressions using the rules from above, our identities. All right. So we want to look at this, and we see that we have a sine to the third, and we got a sine x, and then a cosine squared x. We want to factor. Take out GCF, and that's just sine x. And we have sine squared x plus cosine squared x. The goal is always to see what you can do to get an identity. You always want to see or solve or make an identity. That is always what you want to try to do. And so now that we've done that, sine x, oh, well, guess what? That is an identity. That is the same as 1. And so sine x times 1 is just sine x. And that is your final answer. Okay, number 4. Woo, this one's a little bit trickier. We want to figure out what in the world, how can we get an identity from this? Okay, so let's see. We can't factor. Looks like the only thing that we can do is multiply. So we're going to multiply this on the top. You might need to use the box. I'm going to go ahead and do the box because I know most of us have been multiplying with the box. So secant x plus 1 on the top, secant x minus 1 on the side, and multiply secant squared x, and this is going to be plus secant x. This will be minus secant x, and that's minus 1. These two go away because they're the same but different signs, so they cancel each other out. And so we are left with secant squared x minus 1. And that's what we need to write for the top. Secant squared x minus 1. All over sine squared x. Do we have an identity? We do. You have to use that sheet up top. You have to use that. So secant squared x minus 1, or technically your sheet on the back because this is front and back notes. That ends up equaling tangent squared x over sine squared x. And now we got to figure out, okay, how can we rewrite something else so that we can cancel out more stuff so we can have an identity? I'm going to throw equal signs on all of this because all of this essentially is equal. This tangent squared, there's another identity. That is the same thing as sine squared x over cosine squared x. And then all over sine squared x. And then it's like, dang, now what can we do? Oh, we can simplify this fraction situation. This is like having over 1, so we would end up with 2 fractions. Well, you can think of it as sine squared x, cosine squared x, divide, and you just change the symbol to divide. Or the way I show my work is that I'm going to divide, or I'm going to, technically it's dividing, but I'm going to keep the first fraction, change the division sign to multiplication, and flip to make that 1 over sine squared x. And then this goes away. It would be the same thing as if I wrote sine squared x cosine squared x divided by sine squared x and put a 1. And then I would have kept that, which I keep, changed that to multiply, which I changed it, and flipped that to be 1 over sine x squared. It's the exact same thing, except for I write it up and down because it already started out up and down. All right, now we want to solve this. Well, when we are solving these, when you multiply sine squared x, you can cross simplify sine squared x and sine squared x. So this ends up being 1 over cosine squared x. And 1 over cosine squared x. Okay, 1 over cosine x is secant. So then 1 over cosine squared x is secant squared. And that's your answer. Whew. We're going to practice it, of course, but you're going to get so good at it. It's going to be amazing. Next and last two are the official, essentially, proofs. No, these aren't really proofs. You're just solving. I mean, it is proofs. Yeah, it's definitely proofs, sort of, but we are going to solve these. So we want to find all the solutions in the interval 0 to 2 pi and 0 to 360. So we want radians and degrees. That's essentially what it's saying. All right, here we go. We want to try to figure out how to get, we want to simplify this thing down. cosine cubed x over sine x. The way I think about it is, let's get this cosine squared x and make that cosine x all over sine x. Why? Because I know there's no identities with a third power. So let's go ahead and change them to 2 and 1 so that we can maybe simplify it from there, since I know nothing has a third power with an identity. All right, so now I'm looking at it and I'm like, oh, this part right here is an identity if I separate it. So cosine squared x times, and with multiplying, you can literally just pull it apart. That is totally legal in the multiplication world. And we end up with this expression. Well, this part right here is cosine squared x times, oh, that's an identity, cotangent x, which equals cotangent x. And now I solve for cosecant squared x because, oh, I see that cotangent over there. So I'm going to divide by cotangent x on both sides. This ends up going away. This ends up, oh, it doesn't technically go away. It simplifies to equal 1. So cosine squared x times 1 is just cosine squared x. And over here to the right, cotangent x divided by cotangent x is also 1. But we can't just, make the 1 disappear because there's nothing else there. We got to keep the 1 on that side. All right, now let's get cosine by itself. Oh, square root both sides to get that cosine as a single cosine. So that's cosine x equals what? Square root of 1. Don't forget, plus or minus always attaches with square roots of 1. And now you are thinking, okay, to solve it and keep going, x by itself, cosine inverse of plus or minus 1. And so you have to think to yourself, what angle is the cosine plus 1, 0, and negative 1, 0? That is what you are asking yourself. And I'm going to do a little picture. Positive 1, 0 is right here. Negative 1, 0 is here. And so x equals, well, in radians, it's 0 and pi. And in degrees, that is 0 and 180. And that's the final answer. That was a lot. We had to get some identities going on. And then once we got a single trig function, then we had to get x by itself. That is the goal. So let's do another one. This one is really, really different. This one has 3 terms technically. And whenever you see 3 terms, you want to think factor trinomial. And the way you're going to factor trinomial is with headphones or big X, however you decide. But we are going to let x equal sine x. That's like very, very important. Let x equal sine x. So if we were to let x equal sine x, this is going to be 2x squared, because that's sine squared. So if a single sine is x, then a squared sine would be x squared, plus x equals 1. And now we see, hopefully you can see a trinomial happening. 2x squared plus x minus 1 equals 0. And then we're going to solve by factoring. The way I factor, I do headphones. 2 times negative 1 is negative 2. And we multiply 1 times 2. I know I'm going to subtract to get it. And I need my bigger number to be positive because my middle number is positive. And so we have x minus 1 times x plus 2. We want to reduce and slide by 2. That 2 in the front. This one will have to slide. This one will have to reduce. And so this is 2x minus 1 times x plus 1. And then you set each term equal to 0. 2x minus 1 equals 0, just like with factoring. X plus 1 equals 0. So over here, x equals 1/2. Over here, x equals negative 1. And now that we have this single x, we're going to take it back to the trig function. Sine of x equals 1/2, and sine of x equals -1. And so you're essentially going to solve for x yet again. So this is x is sine inverse of 1/2, and this is x is sine inverse of -1. So what angle is the sine 1/2? And you know this could be plus or minus square root of 3/2. And over here, it is what angle is the sine -1, and that has to be 0. I'm going to draw a little picture so I can figure out, like, space-wise, where is that? Well, square root of 3/2 on the unit circle, and 1/2 would be here. That would be the positive version. Negative square root of 3/2 and 1/2, that would be over here. That would be the negative version. And 0, -1 is here. And so you have 3 answers in all. We want to put them in radians and in degrees. So our first answer, this one is going to be pi over 6. Oh, not 2. This one's going to be pi, and it's 5 pi over 6, because it's 1 less in that quadrant. Your numerators are 1 less than the denominator. And then this one is 3 pi over 2. And with our degrees, well, pi over 6 is the same thing as 30 degrees. 5 pi over 6 is 150 degrees. And 3 pi over 2 is 270 degrees. And this is your final answer. All right, this concludes your notes for day 4. You can do it. Re-watch this video. Listen to this video. Listen to this video. And make sure you take your notes. Good luck, and Marshall out.